In this video, we'll take a look at algebraic multiplicity of eigenvalues. Let's find all the eigenvalues of the given matrix A and their algebraic multiplicities. To find the eigenvalues, we'll take the determinant of the matrix A minus lambda I, and we'll set that equal to 0. The shortcut for calculating A minus lambda I, what we're going to do is subtract lambda from the diagonal entries. So I usually like to do that first, just so I don't make any errors in that part. So we've subtracted the lambdas, and all the other entries in that matrix will remain the same. So there's our determinant, and that's equal to 0. Now to compute that determinant, let's do cofactor expansion along the top row. And let's remember the checkerboard pattern for the signs. The entry in the upper left is associated with no sign change. As you move down or to the right, you've got sign changes. Our cofactor expansion looks like minus 3 minus lambda times the following 2 by 2 determinant. We're just imagining crossing out that first row and that first column. Then moving to the second entry in the cofactor expansion, that 1 gets a sign change, so it's negative 1 times the following 2 by 2 determinant. Then our final entry would look like plus 0 times the appropriate 2 by 2 determinant, and that's going to work out to 0. So we don't even need that entry technically, or that term in our expression. So we've got minus 3 minus lambda times the following 2 by 2 determinant. We'll multiply it minus 3 minus lambda times 1 minus lambda, and then subtracting off the product of 1 times negative 5. So that's going to give us a plus 5. And then we've got minus 1 times, it's going to be 0 minus 2, gives us negative 2. So that entire expression there is equal to 0. Now we'll want to expand and collect like terms. So let's clean up this quantity inside the brackets here. We've got minus 3 minus lambda times, inside the brackets we've got lambda squared. We've got a plus 3 lambda and a minus lambda gives us plus 2 lambda. And for the constants, we've got a minus 3 plus the 5 gives us plus 2. And that's going to get added to the plus 2, and that expression is equal to 0. So let's distribute the negative 3. We've got minus 3 lambda squared minus 6 lambda minus 6, and then we'll distribute the minus lambda cubed minus 2 lambda squared minus 2 lambda, and then plus the 2 is equal to 0. So if we collect like terms here, we've got a minus lambda squared, or minus lambda cubed rather. If we look at our lambda squared terms, we've got minus 5 lambda squared. We've got minus 6 lambda and another minus 2 lambda gives us minus 8 lambda. And then a minus 6 plus 2 gives us minus 4. And that's equal to 0. So now I think I'll divide through by negative 1. And what that's going to do is just create a leading coefficient of 1, which will be slightly easier to work with. So we'll have lambda cubed plus 5 lambda squared plus 8 lambda plus 4, and we'll also be dividing the right side by -1. 0 by -1 is going to give us 0. So I'm going to put a box around this, and now we can concentrate on finding the roots of this polynomial. Let's refer to what's called the integer roots theorem. It says if a polynomial has integer coefficients and leading coefficient equal to plus or minus 1, then any integer roots are divisors of the constant. So our polynomial here, yes, it has integer coefficients, and yep, the leading coefficient is either plus or minus 1. So we can apply this theorem, and that tells us that any possible integer roots would have to be divisors of 4. So we could have either plus or minus 1, plus or minus 2, or plus or minus 4 would be the possible integer roots. So let's go through and check these possibilities systematically. First, let's check lambda equals +1. So we'll plug that into our equation. We'd have 1 cubed plus 5 times 1 squared plus 8 times 1 plus 4. No, that does not equal 0. So lambda equal 1 is not a root. Now let's try lambda equal -1. If we plug that into our polynomial, we've got -1 plus 5 minus 8 plus 4. That does work out to 0. So yes, lambda equal -1 is a root of our polynomial. Now if lambda equal -1 is a root, then that tells us that lambda plus 1 must be a factor of that polynomial. That's the only way that lambda equal -1 would cause that left side to equal 0. So we've got lambda plus 1 times something is equal to 0. And let's find the second factor by long division. So we'll take our polynomial, lambda cubed plus 5 lambda squared plus 8 lambda plus 4, and we're going to divide it by lambda plus 1. So we're going to ask how many times does lambda go into lambda cubed? Well, we go in lambda squared times. We're just really going lambda cubed divided by lambda gives us lambda squared. And now we're going to multiply lambda squared by our divisor. That's going to give us lambda cubed plus lambda squared. And we're going to subtract off what we've just accounted for. So subtracting off, we'd have no lambda cubes, 4 lambda squareds, and we've still got 8 lambda plus 4. So we're now going to repeat the process. We're going to take 4 lambda squared, divide it by our leading term here, our lambda, and that's going to go in 4 lambda times, and then we multiply our 4 lambda by our divisor to get 4 lambda squared plus 4 lambda. We'll subtract that off because that's now all been accounted for. So we've got no lambda squareds now, we've got 4 lambda plus 4, and we'll do the division one final time. 4 lambda now divided by lambda gives us 4. We'll multiply that 4 by our divisor, which gives us 4 lambda plus 4, and we'll subtract that off. So we're seeing that we do get a remainder of 0 here, and we could have predicted that at the beginning. We knew that lambda plus 1 was going to be a factor of our polynomial. So the fact that the remainder is 0, that really just is a partial check on our algebra, making sure that everything looks okay here. So let's go back up to our equation here, and we've now found our second factor. So we can write lambda plus 1 times lambda squared plus 4 lambda plus 4 is equal to 0. And to find our eigenvalues, last thing we'll do is just factor this fully. So we're going to factor this quadratic, and that will factor as lambda plus 2 all squared. So there we go. I'll put a box around that. At this point, we can write down the roots of our polynomial. So lambda is equal to -1 or -2, and those are the eigenvalues for the matrix A. Now the last thing that we need to do is state the algebraic multiplicities for each eigenvalue. The algebraic multiplicity of an eigenvalue is defined as the exponent on the appropriate factor in the characteristic equation. So the characteristic equation is this equation here that gives us our eigenvalues, and we're told that we're interested in the exponents. So let me first state the exponent on that first factor explicitly. The exponent on the first factor is 1, the exponent on the second factor is 2. So we can say that the algebraic multiplicity of lambda equal -1 is 1. That is the exponent on the relevant factor. And the algebraic multiplicity of lambda equal -2 is 2, since the exponent on the relevant factor is 2. At this point, we've completely answered the question, but what I'd like to do is make a connection with geometric multiplicity. The geometric multiplicity of an eigenvalue is defined as the dimension of the eigenspace, or if you state that differently, the number of basis vectors in the eigenspace. For any eigenvalue, it's always true that the geometric multiplicity is somewhere between 1 and the algebraic multiplicity. So if we go back to our particular example here, we knew that the algebraic multiplicity of our first eigenvalue was 1. So that tells us something about the geometric multiplicity. The geometric multiplicity of lambda equal -1 must also be 1, because it's squeezed between 1 and the value of the algebraic multiplicity, which is 1. Now, when we think about our second eigenvalue, lambda equal -2, there's a little bit of uncertainty here, because when we go up to our algebraic multiplicity, remember it was 2, so the geometric multiplicity of lambda equal -2 is either 1 or 2. So without even looking at the eigenspaces, we already have some information about the dimension of the eigenspaces, meaning some information about how many basis vectors we'll find in those eigenspaces.